Welcome to Mission Control, everyone. I am your flight director, and today we are initiating a high-stakes, maximum-yield launch simulation. Our target? Cracking the code on one of the most notoriously unforgiving sectors of the Cambridge AS and A-level Mathematics 9709 syllabus. We are navigating the treacherous atmospheric layers of trigonometry, specifically the compound angle formula. We're talking sine A plus or minus B, cosine A plus or minus B, and tangent A plus or minus B. If you've ever stared at a past paper and felt like these equations were generating a system failure, you are securely locked into the right flight deck. Today, we are treating the syllabus like a critical flight protocol, zero margin for error. Joining me on the console to monitor our telemetry are my top engineers. Alex, what's our propulsion status? Propulsion systems are online, Director. I've got the raw data logs and every textbook definition loaded into the primary fuel cells. We have a massive amount of theoretical fuel ready to burn. Good. Keep an eye on those fuel gauges, Alex. We can't afford to burn all our time fuel on raw data alone. Sam, talk to me about navigation. Navigation is locked and loaded, Director. I've mapped the fastest possible trajectory to the final answer. I'm ready to steer us right through these geometry coordinates at maximum velocity. Copy that, Sam, but remember your structural boundaries. Moving too fast without plotting your command word constraints will tear this mission apart. All right, team, buckle in. Calibrate your screens, and let's optimize this exam trajectory.
Let's initiate our pre-flight briefing with intercepted telemetry straight from the examiner's headquarters. Read this data string with me. Most students lose easy marks on trigonometry, but after this explainer, you won't be one of them. This is our primary mission objective today. The raw data from official principal examiner reports shows us the exact coordinates where candidates experience structural failure. And the beautiful part? These are completely avoidable atmospheric anomalies. We aren't just memorizing mathematical operations today, we are engineering a masterclass in how to pass a Cambridge exam with maximum efficiency. By the time our thrusters cool down, you're going to have an unstoppable strategic advantage over the rest of the testing field.
Here is the official examiner's blueprint to get your payload into that top-tier A-star orbit. First, mastering core math principles. Second, the method mark strategy. Third, top 3 examiner warnings. And finally, advanced exam evaluation skills. The flight path is set. Let's initiate Phase 1.
Flight Director, Act 1. Calibrating the launch track. We are projecting the target orbit profile onto the central viewing monitor right now.
When you are launching into A-level trigonometry, it's incredibly easy to let your systems get bogged down by memorizing superficial data points. But Cambridge isn't just checking your memory banks. They are demanding a perfectly structured logical sequence. The examiners assess exactly 3 distinct cognitive domains, otherwise known as assessment objectives. We need all 3 engines firing in sequence: knowledge, application, and analysis. Director, I've got the knowledge engine fully primed. I can dump every single expansion formula onto the page in the first 3 minutes of the exam. Sine A plus B equals sine A cosine B plus cosine A sine B. Hold your horses, Alex. If you just dump raw facts, you're only firing engine 1. That's a low-altitude descriptive trajectory. You're going to burn all your energy and stall out before you even reach the application phase. That's why I say we skip the data dump, Director. Let's just calculate the final angle and punch it straight into orbit. Analysis engine only. Negative, Sam. You cannot bypass the application layer. If you ignore the structural sequence, you won't establish the analytical logic string required to secure the high-tier marking bands. Both of you need to synchronize.
Take a look at the telemetry comparison on the monitor. This brilliantly illustrates the difference between an average flight and an elite launch sequence. On the left is Alex's descriptive trajectory, superficial breadth, just listing the expanded formula for cosine A minus B without explicitly linking it to the geometric data given in the question prompt. On the right, we have the evaluative pathway, representing true analytical depth. This is where a candidate evaluates the complex geometry, deliberately selects the right compound angle formula, and builds a logical argument step by step.
Director? I'm getting a massive red flashing system failure alert on my dashboard. What's happening?
You just triggered a command word violation, Sam. The system detected that you ignored the word hence in part B of the question. When Cambridge says hence, you must use the evaluative pathway you just built in part A. You tried to steer the flight layout incredibly fast from scratch, and you ignored the structural boundary coordinates. This is exactly how missions fail.
To ensure we stay locked onto that evaluative pathway and clear the atmospheric limits, your theoretical architecture needs to rest on these 3 high-grade titanium pillars: precise definitions, causal relationships, and cross-topic integration.
Cross-topic integration? Director, you mean blending 2 completely different syllabus modules into one payload?
Exactly, Alex. It's a massive secret weapon. Principal examiner reports explicitly state that candidates who successfully navigate cross-topic connections see their propulsion meters peak at the highest marks.
So if I'm navigating a nasty calculus integration problem, and the only way to crack the integral is to first apply a cosine double angle formula derived from the compound angle formula?
Boom! Target destroyed. That is cross-topic integration. You are proving to the mission command that you don't just see math in isolated silos. You understand the mechanics of the entire unified system.
Moving to Act 2, the pure telemetry coordination debate, we are opening up the method mark strategy protocols.
All right, team. This is where we shift from theoretical physics to real high-pressure exam tactics. If you ever feel your heart rate spike because you're terrified a tiny arithmetic error is going to blow up your whole response, you need to hardwire this definition into your mainframe. The method mark strategy is all about earning exam credit for demonstrating the correct analytical process, even if your final mathematical calculation is flawed.
But Director, if my final calculation is wrong, the entire structure is compromised. I have to spend 10 minutes double-checking every single negative sign.
Alex, if you do that, you're going to burn through your time fuel way too fast.
See, Alex? That's why I just write the final answer. If I get it right, I get full marks anyway, and I save the time fuel.
Wrong again, Sam. If you don't document your logic strings and you make one minor calculation error, you hit 0 altitude. No method marks. The examiners are actively scanning for your documented process. If you correctly apply the tangent A+B format, but mess up a simple fraction addition at the very end, the mission command will still reward your logical steps.
So how do we guarantee those method marks under strict simulated clock pressure? We deploy this 5-step procedural framework. Let's run a live simulation right now. 60 seconds on the clock. Go. T-minus 60 seconds. Step 1. Deconstruct the question. I'm scanning the text. It's asking for the exact value of sine 75 degrees without using a calculator. Step 2. Extract data. We can't use 75 directly, so I'm splitting the coordinates into standard angles we know, 45 degrees and 30 degrees. Step 3. Select analytical framework. We need a compound angle formula. Since it's sine 45 plus 30, I am loading the sine A plus B framework. I'm writing down the textbook definition stream right now. Sine A cosine B plus cosine A sine B. Step 4. Execute with clear notation. I'm fighting you on this, Alex. We don't need the textbook definition stream. We need the direct analytical logic string. Let's substitute the coordinates immediately to save fuel. Sine 45 times cosine 30 plus cosine 45 times sine 30. Step 5. Present correct terminology. We swap in the exact surd values. Root 2 over 2 multiplied by root 3 over 2 plus root 2 over 2 multiplied by 1/2. Combine the fractions. Root 6 plus root 2 all over 4. And simulation complete. Incredible work, both of you. Alex, you provided the precise structural definitions, and Sam, you forced the direct analytical logic to secure the high-tier bands before the time field hit 0. You treated that question like a strict compliance checklist, and you just secured maximum method marks.
Let's initiate a quick mid-mission pacing break. We have a vital navigation booster straight from subject specialists to help you retain these exact payload structures. I've got this one, Director. To lock in the exact format of these formulae, create a mnemonic using the first letters of the key terms. For the sine compound angle expansion, the pattern alternates. Sine, cosine, cosine, sine. I just remember the sequence sine, cos, cos, sine. And for the cosine expansion, the terms group together and the mathematical sign flips. It's cosine, cosine, sine, sine. Exactly. Find a catchy mnemonic that works for your own neural pathways. Write it at the top of your scratch paper the second the launch clock begins, and you will never second-guess your formatting parameters under pressure.
Flight Director, Act 3, moving into the danger zone. The top 3 examiner warnings. Launch trajectory hold. Freeze all telemetry. Before we deploy this top-band paragraph structure to clear orbit, optimize your educational flight deck. Take a second right now to subscribe to Ace the Exams at Ace the Exams and enable all notifications so you never miss our weekly flight-tested exam hacks, whether you're launching at IGCSE, O-levels, or AS and A-levels. Hit that yellow notification bell on your HUD right now. Director, we have a sudden structural data loss mid-paragraph. Our evidence links are dropping. The trajectory is destabilizing. If we don't fix this, we're looking at a complete mission termination. Calm down, team. I am overriding the console. Let's analyze the top 3 hazards causing this data loss pulled straight from examiner reports. Hazard 1. Forgetting proper formula format. Students mix up the plus and minus signs in the cosine formula. Hazard 2. Sloppy presentation. Dropped negative signs or messy algebraic fractions mask your logic strings.
Hazard 3, contextual malfunction, giving answers not specific to the given context. If they ask for exact terms using surds and you give a rounded decimal, your system fails.
We are going to stabilize this text flow live. I'm deploying a structural power-up framework adapted from mathematical proofs. It's called the Peel structure: point, evidence, explanation, link. The examiner explicitly states, candidates consistently confuse key terminology. Always define terms before using them in extended responses. Let's rewrite this failing-proof response line by line using Peel to secure the structure. I'll start with the point. State the exact identity clearly. We are establishing that tangent A minus B is our primary framework. I've got the evidence. We substitute the exact known boundary coordinates into the framework without skipping steps. Tangent 60 minus tangent 45 divided by 1 plus tangent 60 times tangent 45. Now for explanation. We show the step-by-step algebraic manipulation. We replace tangent 60 with root 3 and tangent 45 with 1. The numerator becomes root 3 minus 1, the denominator becomes 1 plus root 3. And the link, we rationalize the denominator by multiplying top and bottom by the conjugate, linking it back to the exact format demanded by the question prompt. Perfect synchronization. You just converted a chaotic data loss into a perfectly balanced, high-scoring block of mathematical text. Mission stabilized.
Act 4. Advanced Exam Evaluation Skills. I am now handing control over to the audience for the Interactive Viewer Controls Arena.
Welcome to the arena. Challenge 1, the Visual Radar Sweep. I am projecting a complex comparative text case study onto your screens. The 60-second visual countdown timer is running. Here is your objective. To secure those highest-tier A-star evaluative marks, you must extract the single highest-yielding core trend before the display resets. If you look at the left side of the radar, you see identifying similarities. That's a medium-tier maneuver. A good candidate sees two trigonometric models and points out where they intersect. But look at the right side of the radar, identifying limitations and alternative interpretations. This is the elite sector. Are you actively questioning the assumptions? If a model relies on the sine compound angle, what are the domain restrictions? What happens when angle A exceeds 90 degrees? Extracting that limitation is your core trend. Time's up. Radar sweep complete.
Let's initiate Challenge 2, Identify the Logic Malfunction. I'm putting a flawed, medium-tier sample student response paragraph on the board. The student wrote, I used the tangent formula because it had tangents in it, and the answer is 4. Audience, locate the exact line where poor logic drops the overall score. Director, I'm analyzing their logic malfunction right now. They completely failed to evaluate alternatives. And they didn't justify their recommendations with evidence. They just stated a superficial fact. Exactly. Let me use my digital indicator to highlight the discrepancies. To hit the elite marks, your response must do 3 things: evaluate alternatives, compare approaches, and justify recommendations with evidence. The student should have written, while both sine and cosine expansions could technically resolve the coordinates, the tangent compound approach is highly efficient here. By comparing the given data, which exclusively provided opposite and adjacent side lengths, deploying the tangent formula bypasses the need to calculate the hypotenuse, thereby minimizing arithmetic error risk. You see that? That is how you reveal your examiner logic live.
Flight Director, Act 5, Summit reached. Alex, Sam, what are the readings on your propulsion meters? Thrusters at maximum capacity, Director. We are peaking at a confirmed maximum A-star reading. Sam? Flight completion sequence initiated. We have a successful full-mark launch. Excellent work, crew. Before we close the comms, let me distill this entire simulation into 3 universal rules for our viewers. Rule 1, the 3-step question scan. Decode the command words and establish your analytical framework. Rule 2, the fuel budget allocation. Time your execution. Don't burn all your minutes over explaining standard arithmetic, but never skip the logic strings that secure your method marks. Rule 3, the post-launch system review checklist. Check your formula format, verify your algebraic signs, and ensure your final payload matches the specific context requested. Now, it is time for your final orders. Subscribe to Ace the Exams at Ace the Exams. Click that notification bell so you are fully equipped for our weekly grade masterclasses, and drop a comment below sharing exactly which Cambridge subject and level, IGCS, O, AS, or A-level, you are preparing to conquer next. Every past paper you do is a test flight. Apply these protocols and watch your mark yield climb. Mission accomplished. Flight Director, signing off.